Okay, here we go. I guess I'm live. Great. Well, this is just a live stream I set up to ensure that I actually study. I'm not doing this, or I am doing this simply to hold myself accountable to studying for my Physics 2 exam. I'm going to start with circuit transients. Okay. Circuit transients, LC, RC, and RL circuits, and transient behavior. For some key concepts that are needed, it's the magnetic force law for circular motion, making magnetic fields with the Biot-Savart law with moving charge cross product, the current cross product, and the arc methods, and the Maxwell-Ampere law, which goes into special cases such as wire, sheet, and solenoid with real and displacement current and capacitors. Then we also have the Faraday-Lenz law, which goes over moving rectangular coils with directions included for current fields. And we can't forget that we need to know about inductance and inductors with flex current relations, the EMF, di over dt relations, and inductance of a solenoid. And now to get in what is going over in this part of Unit 2, which is inductors, capacitors, resistors, and circuits. So first we have capacitors and inductors and circuits, where we have the EMF sub L is equal to negative L di over dt, which is equal to negative L, which is the negative inductance, d squared q over dt squared, so the second derivative. EMF R is equal to I R, where I is current, which is equal to R dq over dt. I'm assuming right now that Q is equal to the charge. Then we have EMF C, which is EMF capacitor, which is 1 over C multiplied by the integral of I dt, where C is capacitance and I is current, which will equal to QC, which is the charge of the capacitor, over C, which is going to be capacitance. When solving these equations, write the EMF loop equations or its junction equation using the current or charge as convenient. Then solve the differential equation for current or charge. Discharge a capacitor through a resistor. So let's say we have a simple circuit where in this circuit we have a capacitor, and then after the capacitor it's going to be a resistor. Then it loops back around to the capacitor. In this circuit, right after the capacitor, before you hit the resistor, is an arrow that's pointing towards the resistor, labeled as I. This is in the plus direction of the capacitor. Now, if we start with a charge Q0 on the capacitor, we know we have our loop rules after the switch is closed. We can say that VC plus VR is equal to 0. And we can also say that QC over C minus IR, which is current resistance, is equal to 0. Now, because the charge is going to decrease when the current flows clockwise, we can say that I is equal to negative dq C, or sub C, over dt, which will then go to Q, C, or sub C over C plus R D Q sub C over dt equals 0. And then if we continue to solve this, we're eventually going to get down to V sub 0 over R exp, or experimental, I believe that's what that is, I might be wrong on that, multiplied by negative T over RC, because it is an RC circuit. Now, if it's going to charge, we can say that VC is equal to QC over C, VR is equal to IR, which is equal to DQ over DT times R. So then we would want to write the loop law, which would be E plus VR plus VC is equal to 0. So E minus IR minus QC over C is equal to 0. Or DQ over DT plus E over R minus Q over RC is equal to 0. Rewriting that, we can say that DQ is equal to negative E over R minus Q over RC dt. Now, an RC circuit that's charging, we would say that DQ over EC minus Q is equal to DT over RC. Integrate both sides. We would get 1 over RC multiplied by the integral from 0 to t of dt prime is equal to the integral from q sub 0 to q sub t of dq prime over t is equal to q sub f 1 minus the experimental, or exp, a negative t over rc. Now, in a capacitor, resistor circuit, resistor circuit, we can have a graph. What we will find on this graph is that discharging is going to slope down exponentially, and charging is going to slope up exponentially. You can say that charging Q sub t is going to equal to EC 1 minus EXP negative t over RC. And discharging Q sub t is equal to EC, where E is the field and C is capacitance, EXP negative t over RC. So charging has the 1 minus EXP, and discharging is just EC multiplied by EXP. So if you were to simplify the charging equation, I don't know if it would really be simplifying, but if you were to multiply this out, you would get Q sub t, or to charge, sub time is equal to EC minus EC EXP multiplied by the negative t over RC. While discharging, you would get Q of t is equal to EC EXP minus t over RC, where that 1 is essentially just not in the discharging equation. Now let's look at an LR circuit. An LR circuit, of course, is going to be an inductor resistor circuit. If hypothetically you had a parallel circuit where, assuming that you have a plus minus, where the plus side is going into a switch before going into your first resistor, then you have a parallel section with a second resistor that's connecting from the first resistor to ground, and you have an inductor, L1, that's connecting from the first resistor to ground. And of course ground is connected to the minus side, because you would have no voltage on that ground section. If the switch is closed off for a long time, then the current will all be through the inductor with no resistance. You can say that I sub 0 is equal to V sub 1 over R sub 1. When the switch is opened, the inductor will try to maintain the current, but the current must now flow through R sub 2. So we have a graph that has an exponentially decreasing slope, where negative L is equal to di over dt minus R, which is equal to 0. A di over I is equal to negative R over L dt. I sub t is equal to I sub 0 exp negative R L t, where V sub Lt is equal to I sub 0 R exp negative R over Lt. Now, let's say we put a diode instead of a switch into that circuit. The diode would complete the circuit and allow the current to flow when the voltage is positive on the back end of the arrow. If it breaks, the current does not allow the current to flow when the voltage is negative. Now, the LC circuit, a loop rule. Now this is a simple LC circuit where we only have L and C in the circuit in series. Of course, I is going in the direction from the capacitor, or from the inductor to the capacitor, then from the capacitor to the inductor. And EMF is traveling in the opposite direction as I. So we have this loop rule which states that delta V, or the voltage of the circuit, is equal to negative L di over dt minus Q over C, where Q is charge and C is capacitance. This will equal to 0. If we substitute in I is equal to dq over dt, we will get d squared q over dt squared plus 1 over LCQ is equal to 0. Now these can be compared to the mass of a spring equation, if that helps you, where d squared x over dt squared is equal to negative k over mx, where k is the spring constant and m is the mass, and x is, I believe that's position, if I remember back to physics 1 correctly, which is very similar to the inductor capacitor equation, where d squared q over dt squared is equal to negative 1 over LCQ. So we can say that the solution of the LC circuit, Q is equal to big Q cos omega t plus phi, where omega is equal to 1 over square root of LC, and Q is the charge on the capacitor. Now, okay. So now, we're going into AC circuits. Yep. Okay. Studying. AC circuits. And, the good old friend, phasors. This is a unit 16 in unit 2, so 2.16, where it's the 16th thing in the entire course, but it's from unit 2. It's the last section in unit 2. And in the AC circuits section, it will go into harmonic signals, AC devices, and AC circuits, and the good old friend of phasors. Yeah, this is a long one. So, capacitors and inductors in a circuit. First, we know that the EMF of L, so EMF inductor, is equal to negative L di over dt, which is equal to negative L d squared q over dt squared. EMF R, or the EMF of the resistor, is going to equal to IR, which is current times resistance, which is equal to R dq over dt. And of course we have EMF C, which is the EMF of the capacitor, which is equal to 1 over C multiplied by the integral of I dt, which is equal to Q sub C over C, where Q sub C is the charge of the capacitor and C is capacitance. Now, if you're writing out the EMF loop equations or junction equations, you're going to be using the current or charge as convenient. Solve the differential equation for the current and charge next to solve for these in the circuit. Now, a sinusoidal or AC voltage is important for many applications, such as power generation and transmission, step up and down transformers, sound production and manipulation, or communications. In a driven circuit, in many useful applications, the mechanical or electrical systems are driven by harmonic force, or EMF, which was talked about in the last one, being like the mass on a spring, by comparing the mass on the spring equation to the inductor-capacitor equation, where the inductor-capacitor equation is L, which is the inductance, multiplied by d squared q over dt squared, plus 1 over cq is equal to v sub d cos omega t. Wave technology, peak-to-peak amplitude and root mean square. If you would excuse me for a minute, I will be right back. Alright, back to work. Okay. Sorry about that. Now, wave terminology. A peak-to-peak amplitude and root mean squared. So, we know that V sub t is going to equal to V sub m sine omega t. And of course, then V sub m is equal to the amplitude which is equal to the voltage from point to point, or VPP, over 2. Now, root mean squared. V RMS, or the voltage root mean squared, is equal to the square root of the average velocity squared, which is equal to the square root of 1 over t multiplied by the integral from 0 to t of v squared sub t dt. And of course, using that equation, you will simplify it down to V RMS is equal to V sub m over root 2. Phasor representation. A harmonic quantity, V is equal to V sub 0, sine omega t plus phi can be represented as a rotating vector known as a phasor in the following conventions. Number 1, a phasor can rotate in the counterclockwise direction with an angular speed omega. 2, the length of each phasor is proportional to the AC quantity of the amplitude. 3, projection of the phasor on the vertical axis gives the instantaneous value of an AC quantity. Now, when we want to add the instantaneous voltage around the loop, we need to know that V1 sub t is equal to V sub 1 sine omega t. V2 sub t is equal to V2 sine omega t plus phi. And phasor is sort of like a vector. Now, in an AC circuit, so then we have reactance. In an AC circuit, we know that the voltage T is equal to V0 sine omega t. So we also know that the current in an AC circuit is equal to I sub 0, so the starting current, multiplied by sine omega t plus phi. So the ratio of the magnitudes of the capacitor and the inductors is going to be X, which is equal to V sub 0 over I sub 0, which is going to be equal to reactance. The resistance has a unit of ohms, but results in the current being 90 degrees out of phase with the voltage. Kirchhoff's circuit rules still apply. So the voltage rule or loop rule, which is the sum of the charges at a potential V encountered in a complete traverse of any loop of a circuit, must be 0. And the current rule also applies, which is also known as the junction rule, which says all the currents into a given point on a circuit is equal to the sum of all the currents leaving that point. Electrical power enters or exits a device only if the product of the potential change in the current is non-zero. Now, an AC analysis of a resistive load. See, V sub t is equal to V sub r sine omega t. I sub t is equal to V over r, which is equal to V sub r over r sine omega t. So the ratio of current to voltage is the resistance. I is equal to V sub r over r. Well, yeah. So then we have a resistance load, a resistive load, I is equal to V sub r over r. And a capacitive load, X of C is equal to 1 over omega C, and V sub C is equal to I sub C X of C. Please note that in this situation, the current through a capacitor is 90 degrees out of phase with the voltage. An inductive load. An inductive load, we can say that the reactance, X of L, is equal to omega L. And of course, V sub L is equal to I sub L, X of L. Please also note that the current through an inductor is 90 degrees out of phase with the voltage. Power in AC circuits. Power. P sub T. P sub T, or the power, is equal to the I sub T, V sub T. So power is equal to current times voltage. And a resistor, P sub R sub T is equal to IV, which is equal to V sub R squared over R sine squared omega T. And of course, P sub R average, so the average power is equal to the integral V sub R squared over R sine squared omega T dt, which is equal to 1/2 V sub R squared over R, which is equal to VRMS squared over R. Now, in a capacitor, power AC dash capacitor this is going to say that the power of the capacitor PC is equal to IC VC, which is equal to VC squared multiplied by omega C, where omega C sine omega T cos omega T. It's a big equation. So then PC average is equal to 1 over T, or 1 over the period, times the integral of P sub C. As charge oscillates, energy flows into and then out of a capacitor. Power disposition in inductors. There is no power disposition in inductors. So, power AC inductor. There is no power disposition in inductors. The current and voltage of an inductor are also 90 degrees out of phase with each other. The power in the inductor is equal to ILVL, which is equal to VL squared over X of L. This is multiplied by sine omega T cosine omega T, and the power L average is equal to 0 because there's no power dissipation in an inductor. The current is going to oscillate. Energy flows into and then out of an inductor. Now, in an RC circuit, from the phasor analysis, we know that V in terms of I, R, and C. We can then solve for the voltage across each component. In summary, the RLC circuit includes everything you need to know for computation in Physics 2. Driving voltage is V sub S T, which is equal to V0 sine omega T plus phi 0. I sub T, which is the current, is equal to I sine omega T, which results from voltage S and is out of phase. The voltage of the capacitor T, voltage of the capacitor is equal to V sub C sine omega T plus phi C. And for each component, I is equal to V0 over X total, which is equal to V sub T over XC, which is equal to V sub L over XL, which is equal to V sub R over X of R. X of R is equal to R. X of C is equal to 1 over omega C. X of L is equal to omega L. X total is equal to the square root of R squared plus X of C minus X of L squared. And V sub 0 is equal to the square root of V squared sub R plus V sub C minus V sub L squared. And that should be the end of Unit 2. A little bit later tonight, I'm going to hop on and begin my review of Unit 3. I'm going to knock out the first half of Unit 3 at least tonight. And then I will hop back on tomorrow morning again for the second half of Unit 3. If you tuned in, or if you're watching this later, thank you for watching. Once again, this is just me studying. The whole reason why I'm doing it as a live stream is so I can go back and rewatch if I don't understand something, what I was thinking at the time when I did it. The other reason to do it is to hold myself accountable to keep studying and not procrastinate through the studying. Thank you once again if you did tune in.